Okay, guys, this is going to be your last set of notes, and so that's a good thing. We're going to start with some basics on magnetism. Magnets have two poles, the North Pole and the South Pole. This terminology, North and South, has nothing to do with anything inherent in the magnet. It just has to do with the fact that originally we found poles, they were with the North Pole and the South Pole on Earth, and so we kept that. They don't necessarily have to be on opposite sides. For instance, on a horseshoe magnet, they can be on the same side. Uh, Basically, when you're dealing with a magnetic field, a bar magnet produces a magnetic field and it always goes from north to south. Any magnetic field goes from north to south. But on a bar magnet, it looks like this here. Importantly, if you cut a bar magnet in half, it's very important to note that you can't have half a magnet. So if I cut this bar magnet in half, boom, 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 I don't have a north side and a south sided magnet. You cannot have a monopolar magnet, a single poled magnet. So it can't just be north. It's got to be north and south, north and south. So you can't have just a north magnet or just a south magnet. When you split it in half, it ends up becoming a north magnet and a south magnet again. So you end up with two full magnets as opposed to two halves of a magnet. And the reason for this essentially is that the internal structure of a magnet is aligned north-south, 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 all on the inside. And when you split it in half, it maintains that split. There's many more of these, so technically it looks more like this: north-south, 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 keep going. And so when you split it in half, though, you maintain that north-south balance, and so you end up with the north on one side and the south on the other side. By the way, I would show you what a magnetic field looks like in real life at this point, but unfortunately we are not in school right now, so I'm going to have to show you right here. And so if you look here, these are little iron filings. They look like sand, but they're iron. Imagine, if you will, you took a cheese grater and ran a bar across it. You get these little iron filings. That's not what happens, but just imagine that. So you get these little sandy particles, and they line up, and you can see these little sandy particles are creating that same pattern that we saw over here. And then let me show you a bar magnet. Bar magnets, a little bit different, because bar magnets are using, their fields are going like this from north to south, like this. And so you can see that little curvature there. But then you can also see some of them, once they get over here, they're starting to curve around this way and around this way. You can see this one kind of going like that. All right, so those are all from the field lines that are being created. And then finally, I just want to show you this because it's cool. If you have a bar magnet, you can actually see that field line is actually in 3 dimensions. So those field lines are like going out in 3 dimensions. And again, this stuff isn't special. It's just little iron filings. Again, it looks a little like sand, but it's made of iron. All right, so there are 2 types of magnets. One is the permanent magnet, and it's caused by the atomic and internal structure. And we saw this last week. We saw this during the video that was the Veritasium video, where we went over the 4 different ways you can make a magnet. You have the electron structure itself, the atomic structure itself, the orientation within the crystalline structure, and then the orientation of the fields within the material. And so if you want to, you can go rewatch that, but I'm not going to go into a tremendous amount on this because we need to talk about electromagnets. So we've got electromagnets are caused by inducing a magnetic field by having a current flow through a wire. And essentially, you need to know these relationships. The more current or voltage, so the more current or voltage, the more magnetism. And the more coils, so the more coils of wire, the more magnetism you get. And moving current produces a magnetic field, and vice versa. And then finally, changing magnetic fields produce alternating current, and vice versa. So basically what I mean by that is, if you, let me go through these each in turn. If you're creating an electromagnet and you use one battery to create the electromagnet, and then you use two batteries to create the electromagnet, you're going to have more magnetism occur. All right, that's A. So basically, the stronger your source of electricity, the stronger your magnet's going to be. Coils of wire, if you look at this, basically when you make an electromagnet, the simplest way to look, this is a very simple one, and you can do this yourself if you have the material. You get an iron nail, make sure it's iron, and then you wrap some wire around it, usually copper, wrap some copper wire around it, and then you connect it to the battery, and you can actually create a little electromagnet. They are fairly easy to make, so if you want to make one, it's kind of neat to try it. One of the things you can do when you try this is to try wrapping the coil around 5 or 6 times. Try it, see if it can pick anything up, then wrap it around maybe 10 or 20 times, try it, then 50 times and try it. The more times you wrap it, the more magnetism you're going to get out of that electromagnet. It's kind of interesting. It's a neat little experiment to do. The C and D basically involve the relationship between current and magnetic field. Just wrapping the wire around this iron nail doesn't do anything. It's only when you send the current through the wire that you get anything happening. When you send the current through the wire, it induces a magnetic field, which is amplified by the iron nail. All right. Without the current flowing, there is no magnetic field being produced. So when you stop the current flow, if you take this wire off, the thing stops working. A changing magnetic field produces alternating current. So like if you have a magnetic field and you have a current wire, you can create a current. And if you have a moving current, you can create a magnetic field. These things work they work with each other. And they work with each other to do two very important things. And those two very important things we'll talk about next. The first thing is a generator. So a generator is when we take a coil of wire and spin a magnet inside to produce a current. This happens because a changing magnetic field will induce a current in substances like copper. And there's a lovely video here if you want to watch it that does this and does much greater credit to what we're looking at here. But is a quick little look at it. I'm going to try to show it to you with a picture. We've got a picture of a generator here. Now on this one, they are using I said you could spin a magnet inside a coil of copper wire. What they're using is a coil of wire and then spinning that within a magnetic field. It works the same way. You can either spin the wire or you can spin the magnet either way. So if you wanted to, you could have this exact same setup and spin this and it would, or spin the magnet and it would work, or we could spin this and it would work. Either way, you're going to create a electric current. Now, a lot of times, this is just a diagram, so it just shows one wire going through. You'd get very little current there. Oftentimes, whenever you have these in real life, there's like loads of copper wire wrapped around in there, and you can see that in something like this. So what this is I'm going to try to get it up. This is an example of what the wiring on the inside looks like. All of this right here is wiring. I'm going to pull up just a couple more examples so you can see that there's a variety of different ways these can look. So here's another example. Again, look at how much wiring is in those things. And so one more, just so you can see there's a variety of different ways these can look. Here's another one. All these different things basically have that coil of wire there. All right, and so let me bring this back over here. That red right here represents that coil of wire that you're seeing right here. And basically, as long as you're spinning that within the magnetic field, or the magnetic field is spinning around that, you can induce current. That's how essentially all the electricity is produced. You hook up a turbine to this, and you let water pour over the turbine. It spins this here, turns the coil of wire, and then you get electricity. You can do that with a wind generator. You can do it with a dam. You can do it with coal or nuclear power by producing steam and then letting that push the turbine. Tons of ways you can do it, but that's how electricity is produced. Now, let's look at the next type. The next type is a motor. And a motor is when you take a coil of wire with a magnet inside and let electricity flow through the coil. This causes the magnet to spin. This happens because electricity flowing through a wire will create a magnetic field, which reacts to the magnet. So basically, it's the exact opposite of a generator. And again, I said the magnet could spin. You can spin the wire too, just like we could with the generator. Either the magnet or the wire can spin. It doesn't really matter which one. If you're doing the generator, you're wanting to produce a current in the wire. If you're using a motor, you're using the current to produce movement. So let me show you a picture of a generator, of a motor. And one of the things you'll notice about this picture is that it's essentially the same thing as the generator. You're just doing something different. So in the generator, we are using we're spinning something to create electricity, and in this one we're using electricity to create spin. And so it's like two sides of the same coin. A motor and a generator are interchangeable. You could really use a generator as a motor or a motor as a generator with some very, very slight modifications. So again, with the generator, the more coils you have, the more electricity you're going to get out of it, which is why all these different things had way different amounts of coils in the system. Different amounts of coils. They're using that to produce different amounts of electricity. Oh no, okay. Well, I don't know how to get rid of that. Hang on. There we go. They're using different amount of coils to get different amounts of electricity out of it. And then, so that's what a motor is doing. A motor is producing electricity. A motor is producing movement, and a generator is producing electricity. By the way, if if the zombie apocalypse happens, which seems more real than it did before when I made this joke every other year, basically, you go get an alternator out of a car. Alternators are essentially electric generators. You can go get an alternator out of a car, and you can do lots of stuff with that. You can either make a generator or a motor. Assuming YouTube's up still, you could Google, you could YouTube how to do it. Again, these things, these two videos here are useful if you want to know how this works in more detail. They're a lot more than you need to know, but they're still interesting. So feel free to watch that if you're interested in it. The final thing the final thing we need to know about is called a transformer, and these are not the crappy Michael Bay movies. Come at me, they're crappy. But the transformers that we're talking about here are the ones that are outside outside of some of your houses and stuff. Sometimes you'll see a box, especially outside like an apartment complex. A lot of times in neighborhoods, they'll have them on the poles, the electric poles. There'll be a box or like a cylinder that does the transforming. And the reason you do that is it allows you to step up or down voltage from point A to point B. And so the reason you would do this is like usually when they're transmitting electricity to you, the poles are transmitting electricity at a rate way higher than you need. So in this pole, it might be, I don't know, I'm making up a number here, but it might be 5,000 volts. Now, when it gets to your house, it's a lovely house you have. When it gets to your house, you only need, say, 220. Actually, most houses run off of 120 volts or 110 volts. Can't remember which one. One is European and one's American, and for the life of me, I never can keep them straight. So you have to step down that voltage. If you sent 5,000 volts into your house, it would basically cause tons of problems, fires, all kinds of stuff. But what a transformer does is it looks like this. So a transformer looks like this. And what it does is it allows electricity coming in from one side and going out on the other side. And the electricity coming in from one side, basically, depending on how many times you wrap it, if you have a high amount of electricity coming in, then you wrap it fewer times going out, and you're going to have lower electricity. So this is like, this would be high input, and then you have low output. And again, this is super advantageous because it allows you to transmit electricity at really high voltages. And the reason you want to do that is so that you don't lose energy. And then when they get to houses, they can step down that voltage and bring it into the house so that it's safe. Nobody wants 5,000 volts of electricity in the walls. Like, that scene in Jurassic Park where the kid gets shocked. That's what it would look like anytime you plug something in. Not the type of thing most people would want to have happen. So that's a transformer. All right. So these are your three types of things that you'll need to know about electromagnetism. They're the most common thing. There is one other thing that I'll just mention real quick. Have you ever wondered, like you got a car, and this is a great drawing of a car. And then you have those like magnets that come down and pick the car up and carry them off somewhere. If you ever wondered how those magnets worked, how they were able to turn the electricity on and off, the way they're able to turn the electricity on and off is because they're electromagnets. And so it's not a permanent magnet. There's just a big coil of wire in there. And whenever the crane operator turns the electricity on, the magnet turns on, it can pick the car up and then move it to where it wants to go, turn the magnet off, and the car gets dropped. And that's the beauty of an electromagnet, is that you can turn it on and off. And then we can use electromagnetism to do these three important things that are incredibly useful in our world. I mean, without a generator, no one would have electricity in their house, really. Without a motor, electric stuff wouldn't be able to work. You could still get like I think most cars would still work, but they wouldn't have any, air conditioning or radio or anything like that requires electricity. So those things are important. Generators and motors are important there. Motors are also important because if you didn't have a motor, you wouldn't have a fan, which is very important in Houston. And transformers are important because without them, we could not get electricity to each person's house. We'd have to have little generators on each house, which would be both loud and smelly. So anyway, that is the beauty of electromagnetism, and I hope y'all all have a wonderful day and enjoy the fact that this is the last of your notes for the year.